in Texas, we have lots of natural gas wells, right? So in West Texas, there are these big well heads that actually have these like pools of natural gas, literally. And if it's, well below freezing, those pools can actually start to freeze up. You basically just can't get natural gas into the pipelines. So you have basically this whole system where there are just failure points all over the place, right? And so you have power plants that aren't necessarily equipped to keep running. So you have some that are beginning to have to come offline. You have other power plants that aren't receiving natural gas to run, and they're running out of fuel. As we're getting into these really cold temperatures, demand is going through the roof. You also have, and in this case, the temperature is going to be coldest overnight, right? So your heating's going to be through the roof. That's when your demand's going to go really high. So you're not going to have any solar. And then to layer then that last component, you have wind turbines that aren't necessarily weatherized either. And so you're going to have very low wind output.
And not many batteries yet back then.
And in 2021, pretty low total storage installed capacity, yeah.
Hello everybody and welcome back for another instalment of Transmission. In today's episode, Quentin sits down with Modo Energy's ERCOT market lead, Brandt Vermillion. Over the conversation, Brandt touches upon his time in the ERCOT control room, what goes on behind the scenes, and how things are changing for batteries in ERCOT. As always, if you are enjoying the conversation, please don't forget to hit like and subscribe. It really helps us to reach a wider audience. And with that, let's jump in.
Hello, Brandt.
Hey, Q, how's it going?
Very well. Nice to see you again. We actually kind of sit next to each other a lot now.
Yeah.
Nice.
Yeah, that's been a good time. Good transition into the office.
Considering 3 months ago we didn't know each other.
Yeah.
It's pretty mad how much time we spent together. Very excited to have you on the podcast, actually. For our listeners who are interested in ERCOT, you actually bring a very unique perspective, and I'm going to ask you lots and lots of questions today. But before we get started, can you just explain what an RTO is and an ISO is? And for once and for all, explain whether ERCOT is an RTO or an ISO.
Sure, yeah. So the whole idea of an RTO or an ISO is essentially just a nonprofit entity that is essentially overseeing the operations of the electric grid in a given area. So in North America, I want to say there are 7 or 8 different ISOs or RTOs, give or take. And generally so you have like PJM or MISO or CAISO, which some of those are multi-state entities, right? They're overseeing the flow of power in a good number of states. So PJM, I think, is as many as 6, 7 states. MISO's even more. But for ERCOT is actually only overseeing the flow of power within the state of Texas. And so that's generally going to be the distinction between an RTO and an ISO. So those acronyms just being Regional Transmission Operator and I believe Independent System Operator for ISO. So ERCOT is, in fact, just an ISO, given that it's only operating within the state of Texas.
And so in British parlance, a bit like National Grid ESO, or in Europe, an ILIA or something like that, just to put everyone on the same page.
Yeah, exactly.
And so ERCOT, we've done this before, we'll go again. ERCOT stands for?
The Electric Reliability Council, I believe, of Texas. Yeah, so it's essentially just like overseeing both the operations and the market side of the transmission grid in the state. So that's kind of organizing and centrally dispatching generation, as well as working with utilities to look at power flow and essentially how that is, moving from those generation centers to demand centers and ensuring that at least at the transmission level that, all demand is being served, grid staying balanced at 60 hertz, and that the market is clearing efficiently.
What I'm learning from the last 12 months of looking at the US market is you really have to understand maps to get your head around it. Everything's a map, right? Yeah. And so ERCOT is the ISO that covers Texas, almost all of Texas, but not all of it. There's little bits around the edge that it doesn't quite cover, right?
Yeah, exactly. So like El Paso, for example, is probably the biggest like demand center that isn't covered by ERCOT. I believe they're actually part of like WEC, I think. So, and that might actually technically not be an RTO.
Oh, here we go. No,
yeah, yeah. We can get into the blank spots in the map of your ISOs and RTOs, but Yeah, so ERCOT, I believe, serves something like 90% of demand in the state of Texas, and the actual like energy infrastructure that is within the ERCOT network covers actually a little bit less than that in terms of overall land usage. Yeah, there's some pretty large land areas, maybe in like the Panhandle of Texas, that are technically not a part of ERCOT as well. So where there's maybe not quite as much demand, but yeah.
And we're going to talk about ERCOT loads today. But before we get there, I want to talk about you, Brandt. So, yeah, we've been working together about 3 months, and I've just been blown away by how much I've learned by just sitting next to you and by osmosis figuring out the stuff you know. And so, what's your background? You've been at ERCOT for a while. You've come at this from an engineering perspective. Do you want to just talk about what you studied, what you did at ERCOT, and then we're going to deep dive on some bits.
Yeah, so I graduated from college or university in 2019, and then moved down to Texas to go to work for ERCOT, and I studied electrical engineering at school. So yeah, basically I went into like a rotational program with ERCOT itself, kind of getting a sense of what the different engineering teams do, what I like doing, and what maybe I was better at than what I wasn't as good at. So that was a really great experience, about a year long program of just kind of figuring out where I fit best and what I would want to kind of go into. I guess, I mean, I was already full time, but like truly full time. And so from there, I went into working in the actual ERCOT control room. I was basically just a support engineer. I think the title is like shift engineer. So a lot of that was just actually working like, days and night shifts, 12 hours at a time, overseeing grid operations alongside like 7 operators in the control room.
And we've seen the pictures. This is the big room with the walls with all the lights on it and lots of screens and buttons to press and a fairly high stress job with people keeping the lights on.
Yeah, yeah. No, it's pretty much, yeah, it's pretty amazing when you first walk in there. You're kind of blown away. You're almost starstruck, I guess. So yeah, the desks in there have about 8 monitors, and the giant screens at the front that's probably a 40-foot tall. We call it the wall board.
The wall board.
Yeah, it's
I like
just
that.
data everywhere, right? So it's just kind of hard to wrap your head around, but like once you're in there, it's pretty amazing. Like overall, like just fire hose of information, and it's pretty invigorating. Yeah. So there's a lot to do. I mean, there's definitely some slower times, but when it really picks up, it picks up for sure. And it's almost like you're working in a hospital and you're like triaging like what's most important, right, in terms of solving multiple issues at once. And it's a really fun challenge. So.
Where is it? Where is it in Texas? Is it in Austin or is it in Dallas or
Yeah, yeah.
Houston?
So ERCOT they have a couple different offices, but the like primary engineering office is actually up in Taylor, Texas, which is about 25 miles northeast of Austin. And then like the stakeholder meetings and things like that are actually held at a building in Austin proper. So kind of close to the airport. But yeah.
So the control room's in Taylor as well.
Yeah. Yeah. The control room is in Taylor.
And what does this may sound like a stupid question, but what does the control room have to do? What's within the control of the control room?
Right. Yeah. So a lot of what the control room is doing. So right. So I mentioned the 7 other operators. They each kind of have their own individual responsibilities, and a lot of
Seven other operators, sorry, 7 other human beings in the room with you.
yeah, exactly. Yeah. So there's 8 people in there. 7 of them are operators is the title, and usually they have a wealth of industry experience in some level, whether they were working at a power plant earlier in their career, or actually like maybe were linemen or something like that, and eventually graduated to working in maybe a utility control room, and then eventually working at ERCOT. And then there would be somebody like myself working as like an engineer that's maybe a little bit more familiar with the applications that are kind of running all the time. And so that kind of goes into your question, where there's an aspect of it that is essentially just saying, hey, we have this process that's running every 5 minutes, which is, hey, we're basically recalculating power flow so understanding, you know, we're receiving data from generators and utilities that's saying, hey, we're outputting this much power, or we're capable of outputting this much power as well. This is kind of what utilities are seeing, like in terms of their different substations and switching stations, in terms of how much power is being carried on transmission lines and things of that nature, and then therefore actually being distributed to different loads going into the distribution system. So ERCOT's kind of receiving all that data. They have their own energy management system, as a term. Basically, it's kind of a bespoke software that manages the grid essentially, or at least allows you to manage the grid. And so going back to that 5-minute process, right? So you start by calculating power flow, then it goes into what's called contingency analysis, so real-time contingency analysis. And that might be something that might not be as familiar for people coming from the UK, right? Because you guys don't have N-1 security.
No, we don't. Before we jump down there, though,
Yeah.
let's just get our heads in the same place here. So we're talking about a control room with 8 people in it, with loads of screens and loads of computers. And then you're talking about this 5-minute process,
Yeah.
right? Which, what is that? Is that an automated thing that happens, or is it a piece of paper running around? And what do you mean by 5 minutes? As in it happens every 5 minutes, or it takes 5 minutes?
Yeah, so it kicks off every 5 minutes. I think it's on the 2s and 7s in terms of the minutes, the clock minutes, right? Is typically what happens, right? So that starts
Every 5 minutes, 2 minutes and 7s, you have to do this thing to keep the lights on.
Yeah, so it does run automatically. The energy management system is essentially set up so that, every 360 seconds or whatever, 5 minutes, it kicks off. Yeah, so it goes into power flow, which takes about maybe 5 seconds to run. Then contingency analysis, which is maybe more like a minute, minute and a half usually. And then from there, there's an additional part of it that runs every 10 minutes. That's kind of just for like overall like larger voltage stability. And that's where if we wanted to talk about GTCs or generic transmission constraints in ERCOT, that's where those kind of come into play in terms of establishing limits for like these larger interfaces of lines. So it could be a group of, 3 to 10 lines, something like that, where it's like aggregating all the amount of power flowing over those lines. And there's basically new limits that are recalculated for that as part of this process. But that's kind of a digression going back towards the 5-minute process, right? So the kind of conclusion of that is the actual central dispatch of generation within ERCOT. So that's done via security constrained economic dispatch, or SCED. So
security constrained economic dispatch. What does that mean?
Right. So the security constrained aspect of it kind of goes back to that N-1 security thing. So N-1 just being that if you lose any given element within the bulk electric system, so that's, transmission lines, transformers, even generators to some extent, basically what does power flow look like? So you have your base case power flow, right? This is what's actually happening in real time. And then from there, there are contingencies that are within the ERCOT model, right? The network operations model. And those contingencies are saying, all right, well, this transmission line, this element of the bulk electric system will be removed. And then let's recalculate power flow to see if now any other elements become overloaded as the result of that lost element. And so essentially, if the contingency analysis portion of that 5-minute process, if one of the recalculated power flows essentially shows that a transmission line is at risk of becoming overloaded as a result of the loss of another one, then ERCOT is controlling to that essentially. And that's part of that optimization, which is that economic dispatch portion of the acronym, right? So basically that's an additional component beyond so if you think about economic dispatch, right? So your kind of baseline level of that is you're trying to serve all the demand as cheaply and efficiently as possible, right? So that's based on the bids and offer curves
which is pretty much the same system in liberalized energy markets everywhere. Is the same thing where you put all the bids and offers together, or the generating units that can provide power or consume power, and then you figure out the most economic way, the lowest cost way of getting enough power on the grid, right?
Yeah, exactly right. So you have like marginal dispatch is kind of, I think one of the generalized terms for that, right? So you have all this demand, you have all these generators, they all offer in to dispatch or to generate power at various prices, right? And so all things being equal, if there are no other constraints on the system, you're just going to get the cheapest group of generators to, fulfill that demand. Then there are additional constraints that kind of come in on top of that with the generators themselves, right? So if for like CCGTs, for example, or thermal generation, often they'll have
it's gas units, combined cycle gas units.
Yeah, exactly, right. So you'll have like a minimum that they want to output. So that's one type of constraint that would go into that model. So it's saying, all right, well, if I'm going to dispatch this unit to generate at all, they need to supply at least 30 megawatts of power rather than just saying, oh, I'll only get 1 megawatt from them, that type of thing. So that's a baseline constraint. And then from there, you're kind of layering in that contingency analysis and making sure that all elements within the system are protected to some extent. And yeah, so I think that's kind of a good summary of what that economic dispatch looks like. So Yeah. So, and that's how you see some large price variation if we were to get into locational marginal pricing, right?
Oh, we're totally going to go there. But
Yeah. Yeah.
before we get there, so what's ERCOT's control? There's two questions here. So I thought ERCOT was a 15-minute market. So why are you talking about a 5-minute process?
Yeah. So this is kind of an interesting nuanced thing to get into, I guess. So you have every 5 minutes we have that process that happens, right? But the settlement periods in ERCOT are 15 minutes. So essentially what that means is those 15-minute settlement intervals are averaging out 3 5-minute intervals, right? So the whole idea behind that is essentially it can kind of smooth out some of that price variability and price variation that you might have within a given 5-minute period of time. So there are definitely plenty of instances within ERCOT where you have all of a sudden you get a high system level price or system lambda price of multi hundreds of dollars per megawatt or potentially even in the thousands that then drops all the way back down to a more standard level that you might expect, so somewhere in the dozens of dollars per megawatt hour, that type of thing. And so that's kind of not necessarily an extended price spike, and so that might mean that the average for that settlement interval is closer to that more expected or more typical baseline. And I think that's part of the idea of the settlement interval being longer than the dispatch interval, I guess.
And also, things happen faster than every 15 minutes, right? You have to manage the system faster than 15 minutes.
Yeah.
What's interesting about what you've talked about there is you said it's a 5-minute process. So there's a process that runs every 5 minutes that you guys are doing in the control room. But actually, I thought it was interesting that you talked about how long each step took, right? Because one bit of it, the economic dispatch, the putting all the bids and offers together and working out what the least cost amount of power is, you said, I think, if I got it right, you said it took about 5 seconds. And then all the constraint bits, i.e. modeling all the power flows and seeing which lines are going to be overloaded and all the, I guess it's factorial equations to figure out the different ways you can cut the cake, cut the mustard as well. That, I think you said, took about over a minute or 100 seconds or something.
Yeah. The contingency analysis is absolutely the lengthiest portion of that process. The economic dispatch is kind of almost a modern marvel, really. In fact, that optimization is so efficient. I mean,
The reason why is it not to always bring it back to Great Britain, which we need to stop doing in this podcast because we have a lot more US stuff going on. But a lot of our listeners are from Great Britain, and there's an issue with National Grid at the moment. There's like an issue that's been around for a long time about this thing called skip rate, where some assets, you see it, right? We talked about it. Some battery assets, some other assets get skipped, even though they're cheaper, because National Grid, the constraint analysis bit, National Grid needs to focus on the constraint analysis.
Yeah.
But if you had the same computer and one calculation took 5 seconds to do the economic dispatch bit, which is the bit we all understand in Great Britain, and then the constraint analysis takes over 100 seconds, so it's 20 times more computation. And that's a bit that National Grid in the UK says is the hard bit that they need to manage, and that's why things get skipped. It's just, it's very interesting to me to hear it from ERCOT, the kind of the difference in computation there. There's just a lot more to calculate.
Yeah, I mean, I think so. Right. So if we go back to that 5-minute process, it starts with a base case power flow, which is just looking at what does the system in actuality look like right now in real time. And if you layer in the fact that, there are quite a few elements in the bulk collector system, there's, thousands of transmission lines and transformers, right? And theoretically, all of these contingencies, so all of essentially the loss of any of those individual elements, all of those are modeled by ERCOT. Theoretically, that contingency analysis could actually take even longer if you were going to process each and every one of those the loss of each and every one of those elements, right? But there's actually a screening process for the contingencies in ERCOT, which actually helps reduce the amount of time it takes.
Okay.
But if you think about even just with that reduced number of contingencies that are being processed, it still takes, like you said, 20 times as long as just a single power flow and also that economic dispatch portion. So part of that is because, if you think about the number of contingencies that are still being processed and the fact that our original power flow still took, 4 or 5 seconds to compute on its own, even if you're doing 100 contingencies, I think the power flow actually ends up taking less time typically because it's also more, I believe the way it works, we could really get into the weeds on like state estimation and things like that. We don't need to do that, but is that it's essentially the power flow that gets recalculated is localized, I want to say, to the area in which the contingency were to hypothetically occur. So I think that helps, again, reduce computational time. So it's pretty ingenious design in terms of how it all comes together to keep things happening on a 5-minute granularity.
I can't help but think we just need more compute, right? I assume that it runs in AWS or Azure or somewhere in the cloud, or is it running locally?
I think it's run on local servers
Okay.
because then you don't have to rely on Amazon not going down or things of that nature.
Yeah.
So
We need more servers, I think. Let's do it.
yeah,
Let's do it faster.
I think ERCOT's got some pretty substantial server rooms for sure, but you could always use more.
I'm already aware, now we're having this conversation, that we're not going to cover all the things that we said we're going to cover.
Yeah.
And I'm just going to jump around a little bit. Let's talk about, you're in a control room, you got the team with you, and things start to get a bit hairy. Let's talk about some storms that have happened or some of the challenges, because they're hot topics. I mean, everyone in Texas knows ERCOT now after those storms and the blackouts. So
Yeah, maybe
happened?
not. So maybe with some lack of context as well surrounding that too, right? So yeah, so I guess one big thing to point out is that ERCOT doesn't own any physical assets, right? They're just kind of overseeing the operation of everything. So and they're a nonprofit entity, so they stand nothing to gain by power prices being incredibly high or anything like that, which I think was, at least among maybe some of the general public, kind of a common misconception.
The ERCOT was profiteering.
Yeah,
from-
yeah. Yeah, there was some amount of ERCOT is responsible for this in the sense of, they're trying to make money off of this essentially, which, yeah, I mean, I think that's probably hopefully commonly understood now that that's not the case. But beyond that, yeah, so the control room can definitely get to be a pretty wild place, when things are hitting the fan, no doubt, where you have different people that are trying to kind of perform their own job. So, you have somebody who's just trying to manage frequency. You have people that are trying to mitigate congestion and severe transmission issues on the system that basically can't be handled by the economic dispatch.
So the 5-minute thing's running, and then there's bits that even the computer can't handle, and so the people have to come and do.
Yeah. So basically, yeah, to explain what that would be is you can have an individual constraint that is essentially just very hard to resolve. And the way that comes about typically is
Give me an example, sorry, because we're talking, feels very meta, this conversation. So what
Yeah.
would be a typical constraint in ERCOT?
Usually the typical ones are actually feasible to resolve, I guess. So a typical constraint, we could just call like the west to east transfer, essentially, or WestX is the name of the GTC, or if, I know we like our acronyms in America, so I'll try to spell them out, but generic transmission constraint, or IROL, or interconnection reliability operating limit, I think is what it is, which is actually a NERC term for another one for you. So the North American Electric Reliability Council.
But WestX,
WestX.
getting power from the west to the east.
Yeah. So, it's a group of lines that are trying to take, all this wind and solar generation that's out in West Texas and get it to the demand centers. If you have quite a bit of wind, it's a very windy day, combined with a pretty sunny day where there's, as of now, we're talking teens of gigawatts. So 15,000 megawatts maybe of solar at the same time. It's quite a lot of power to get from maybe some sparser population centers in West Texas to your Dallas, Austin, San Antonio, Houston population centers.
Yeah,
If
you're looking on a map, if you haven't looked at a map of Texas, which is fine, no one's expected to know everything, but generally demand centers are on the right. So you've got Dallas, Fort Worth, Houston, Austin, San Antonio on the kind of east side, and on the west, Texas is a vast space. And on the west side, you have this huge open land, kind of desert-y kind of area. And there's tons and tons of generation there, like wind and solar. And so you've got to get that from the west to the east. And that's what we're talking about now.
Exactly. And so high level, that's one of the most common constraints in ERCOT is that you see as being at risk of overload, essentially, where, yeah, so you only have so much transmission capacity to move all this power. And ERCOT has to essentially be aware of how much power is flowing over those transmission lines. And if that group of lines exceeds a certain limit that is imposed by ERCOT, essentially, that has been studied via like stability analysis studies, then they're going to have to curtail generation on the other side of that constraint. So they're going to curtail.
Turn down generation.
Right. So
we're
they're
talking
going
about lines. We're talking about overhead lines. This is overhead lines connected by to pylons. Yeah. Above ground, right? Lots and lots of them.
So your high voltage transmission lines, like, the giant towers you'll see if you're driving on the highway, for instance. Yeah, so we're talking about like 345 kilovolt lines. And yeah, so if those are essentially, getting closer to that limit that's studied by ERCOT, and that's when we see generation begin to be reduced, right, in West Texas. And often your wind and solar generation is going to be lower on that marginal cost stack, just based on where they tend to offer in. And so they will typically be almost always will just be dispatched to meet pretty much the base load, even like your minimum demand in Texas. It basically will, assuming no constraints, you'll see all of the wind and solar online. But once you introduce the transmission constraints element, that's when you start to see potentially on the order of thousands of megawatts of wind and solar generation curtailed. Right. So, yeah, so that's a common constraint in ERCOT. But if we go back to the idea of irresolvable constraints, typically what that would be is just kind of a tricky transmission pocket, essentially. So there's maybe often what that might look like is there's not very much generation near it. And so why I say that is because, the closer electrically in particular, so the closer topologically, if we think about a map rather than geographically,
Yeah.
just in terms of, you have a node here and a node here, it might be, within a couple of nodes essentially of this potentially overloaded element, right? And the closer that generation is, the more likely a higher percentage of that marginal megawatt that can be produced by that generation is going to flow over this potentially overloaded element. So if we're very far from a high amount of generation, often this will happen on lower voltage lines in particular because they tend to be electrically further away.
What's lower voltage in numbers?
So the three main transmission level voltages in ERCOT are 69 kilovolts, 138 kilovolts, and 345 kilovolts. So yeah, those are generally, so low voltage in this case would generally be 69. Yeah. So often that'll be a case, that'll be the type of case where you'll see these irresolvable constraints. And essentially, right, so you have this generation that's a little bit further away, and therefore the marginal megawatt produced by this generation has pretty minimal impact on the flow on this potentially overloaded line. And similarly,
The marginal megawatt. Let's just break it down. So,
yeah, we can break that down.
so let's say a gas peaking plant, they can generate a bit more. So the marginal megawatt. So a gas peaking plant is running, and they can do another megawatt. And what we're saying is that additional megawatt is what we care about. The difference, the delta,
Yeah.
that is.
Yeah. So essentially, this goes back. If we go all the way back to the economic dispatch, right? And we think about how the price of power is derived, essentially. So, you have that system level price, a system lambda. That's just generally the cost of the idea behind that is it's the marginal cost of power on the system. And if we break that down further into the locational prices, so you have all these different nodes across the state, and each of those receives a locational marginal price. So essentially that's what, if you had a generator at that node, that's the price that they would receive at the given point in time. And so if you have separation between that system level price or system lambda and the node that your generator is sited at, so your LMP that you're receiving, your marginal price at that location, that is generally going to be caused by congestion or some overloaded element across the system, or potentially overloaded element if we go back to that N-1 concept.
Yeah, because it's not necessarily about overloaded elements. It's about what might be overloaded in this concept of N-1, which is crucial to how we think about this.
Yeah, exactly.
Because you're actually solving problems that don't necessarily exist yet in some cases.
It's about, getting ahead of problems before they happen, right? And ensuring that, a problem that ends up, if it happens, it ends up being maybe more small or minor or easily resolved, isn't actually, a very large problem that can be even potentially begin to cascade. You're just getting ahead of things, right?
And what does that actually mean then? So I know we're jumping around here, but so N-1, what I think I know what that means, but I'm only 80% sure. Does that mean that any line can go down at any point and the system stays on? Is that how it works? Or
That's the idea.
Everything is only at 50% load all the time? Or is it something else?
Yeah, so really the idea is kind of like you had just said, is that you can lose any one element on the system and the system is just still fine. It's still able to operate. There's no, crisis occurring. There's no potential cause for emergency. Ideally, the control room is still in a quality state. And in terms of there's no, there's no sweat dropping off foreheads or anything like that. if you lose any one element of the system, right? You're prepared for all outcomes, or any, not maybe not all, but any within the realm of one element being lost, right? So yeah, that's functionally the idea behind it. Is really just to ensure preparedness in the case of losing any one element. Yeah.
I mean, it totally makes sense, of course, but it's one hell of an overhead, right?
Yeah, yeah. I mean, it's quite the remit, right? In terms of being able to control for that. I mean, there's a lot of possibilities within, thousands of elements that could be lost, and then what does the system look like as a result? Yeah,
So can you tell us what happened in Storm Uri? Can you well, just a bit of background on what Uri was
yeah.
and why it matters so much, and a bit of a blow by blow account of what happened and why it was significant.
Right. Well, that could be a whole podcast series, but
Well, maybe we'll come back to it another time. But yeah, in a nutshell,
in a
but also
nutshell,
with lots of detail.
yeah, because part of it is because I don't want to just say, oh, well, it was all this sector of the industry that brought, the system, on to the verge of basically. But I mean, if you want to begin, let's just say Texas is not used to it getting very cold, right? And so, heading into, I think it was like right around Valentine's Day in February of 2021. So heading into that week, I think Sunday night was the first night where temperatures really began to drop off. And we're talking as low as around 0 degrees Fahrenheit, so well into the negatives in Celsius, which Texas very rarely sees below freezing temperatures. Really, it's not often the case that it gets much below 40 degrees Fahrenheit or just single digit Celsius, right? So I mean, when you're seeing 5 degrees Fahrenheit on the forecast in Texas, that's already alarm bells to begin with, right?
Yeah.
And so part of that is because demand is obviously going to go very high in that case, as it would in most places that even that would typically see that level of temperature. But beyond that, Texas is not really prepared to keep houses warm, right? It's houses here are built more to retain cool air in the summer and keep houses cool rather than to retain heat in the winter. So you have that. You have the fact that a lot of homes have electric heating rather than gas heating, which this is very engineering heavy, but you get into some resistive heating, which essentially to keep beyond a certain level of loading for those heating elements, they become much less efficient.
Mm.
And so they take more power essentially to function. So that can drive demand further. There's some really good academic studies on that. But so that's a component. You have
There's some non-linear components here as well.
so there's that. So essentially, right, you have really high demand. You're looking at that.
What does that mean by high demand? What is that?
Right.
Is that 10 gigawatts, 100 gigawatts? What is it?
Yeah, so for Texas, that would just be, we're talking, I think at the time, that was probably more in the 70 something gigawatt range. We were maybe looking at over 80 for that week.
So
didn't quite end up getting there, but
almost twice the peak demand of Great Britain on a very cold night.
yeah. And yeah, this past summer in 2023 in Texas, I think peak demand got probably a couple gigawatts over 80 megawatts. So that would have been the new record demand or whatever you want to call it. Yeah. So yeah, just for that context, right? So then the next element, right, is you have, so I guess just for an additional contextual point, generally with the fuel mix in Texas, natural gas, I would say this is kind of a ballpark number, but I'll say it's maybe around 40% of demand typically throughout the entire operating year. That's just based on the last couple of years.
Natural gas, as in natural gas power station.
Yes.
Oh,
Yeah.
okay.
In terms of if you're going to break down your fuel mix by natural gas, wind, solar, that type of thing, natural gas, I would say is probably in the 40 to 50% range.
Okay.
So if you think about, if you have, your 80 gigawatt peak demand that you're expecting, then by nature, you're hoping to have it actually in this case, it's probably going to be even higher amount of natural gas generation because typically in really cold conditions, if it's cloudier outside and wind turbines aren't necessarily equipped to handle like 0 degree weather as much, especially here in Texas where they haven't necessarily been weatherproofed as much as they might be for an offshore wind farm
Yeah.
off the coast of GB or whatever. But yeah, so you're going to have a high proportion of natural gas generation. Those natural gas generators are, again, built with summer in mind rather than winter. And so you have a lot of instrumentation and cooling elements that are actually housed outside, right, to help keep them cooler in the summer rather than warmer in the winter, where they might be built in a big brick building somewhere. And if you were talking about like in the northeast of the US and New England, so all your natural gas generators are just built in a completely different way.
So some of the gas plant wasn't planning to run, well, isn't really designed to be run at such cold temperatures as well.
Yeah, in Texas. So you have that elements of it. There was maybe a lack of weatherization for cold weather as well. Like, so lack of preparedness in that sense for some of the natural gas generators. That's a component. That's definitely not every natural gas generator, but it definitely happened. And then going further into the natural gas side of things, you have the actual gas industry itself and the transmission of fuel to those power plants. So that's both in the pipelines and as well all the way back to, in Texas, we have lots of natural gas wells, right? So in West Texas, there are these big well heads that actually have these like pools of natural gas, literally. And if it's, well below freezing, those pools can actually start to freeze up and you basically just can't get natural gas into the pipelines. So you have basically this whole system where there are just failure points all over the place, right? And so you have power plants that aren't necessarily equipped to keep running. So you have some that are beginning to have to come offline. You have other power plants that aren't receiving natural gas to run and they're running out of fuel as we're getting into these really cold temperatures. Demand is going through the roof. And then you also have
squeezed on all sides.
You also have, and in this case, the temperature is going to be coldest overnight, right? So your heating's going to be through the roof. That's when your demand's going to go really high. So you're not going to have any solar. And then to layer then that last component, you have wind turbines that aren't necessarily weatherized either. And so you're going to have very low wind output.
And not many batteries yet back then.
And in 2021, pretty low total storage installed capacity. Yeah. So maybe on the order of maybe 500 megawatts, a ballpark. It's somewhere in that range, definitely less than a gigawatt.
Not in the multi-gig that we're in right now.
Right, and growing too, yeah. So, yeah, in that context, kind of just a perfectly imperfect storm, right? So you have all of these different elements kind of coming together to working in concert to really throw the best punch Mother Nature has to offer at the power grid.
So it's coming up to Valentine's Day. The cold weather's coming in. You have all these different scenarios which are squeezing the system as a whole. At what point, what's happening at ERCOT at this time?
Yeah, it's very much an all hands on deck situation in terms of, so for me, I was, I think I was going into my second full-time shift as a shift engineer. So it was a real trial by fire situation for sure. So yeah, I think I'd gotten NERC certified. You have to pass a test to be able to go into the control room, actually do things. And I started training in like October of 2020. And so yeah, I think it was my second full-time shift rotation going into that week.
So you're the scapegoat.
Yeah, it's me. I press the big red button.
Yeah.
Yeah, at ERCOT, you have, you kind of are getting reserve crews to kind of help out and run additional power flow studies and things like that to help troubleshoot all these like additional like congestion issues or, trying to resolve constraints essentially that are irresolvable by the economic dispatch. You have a lot of that going on. And so it's maybe more than a typical crew would be able to handle effectively and efficiently in the control room. So you kind of have additional support being called in terms of, people kind of in the back room running support studies, right? To kind of help say, hey, we have this issue. Can you run the studies for it? And basically just give us a solution that we just kind of have in our back pocket, because a lot of these are N-1 situations, right? So if you're controlling for something that hasn't happened yet, you basically just, a lot of that is just having a plan to resolve the issue if it does occur. And so that's what all these studies are being conducted for, is you just need to have something on record to say, well, we know what we're going to do if this happens. And then we have this overload that we have to deal with quickly. And it's just all about preparedness. So you have a lot of that going on. You also just have, so we have, if we go back to like the GTCs and so
the constraints,
your larger interfaces of constraints that are across multiple transmission lines. So those, typically a transmission line has a limit that's just supplied by the utility, right? So if it's 138 kV line, maybe that limits, it can handle 400 MVA or essentially 400 megawatts, but with the reactive power is MVA, right? So it can handle that much flow across that line. But if you group them together, that's when you have an interface is what they call it. And that's like how that West X constraint is derived, is you have a group of like 10 different transmission lines, but you can't necessarily just add up all of their transmission, like thermal transmission limits together, because that's actually going to be a larger number than the limit that ends up being supplied by ERCOT, because when you have this really large transfer of power across a large geographical area, you can run into like voltage stability and transient stability issues, which is, that's super engineering heavy. But
inductor, right? But from west to east.
Yeah, you have huge voltage sag essentially, which for maybe non-engineering types is essentially just, that's potentially very bad. And can cause...
it's different, slightly different, but we have it in transmission lines in Great Britain from the kind of supergrid out to the west of Wales or the west of Cumbria. We have the same thing, but I mean, we're talking about like 1/20th of the distance here, and certainly not the same power. But it's everywhere. It's everywhere.
Kind of lost where we were at. Where are we coming back to?
Right, yeah, good point. We're talking about Uri. So Storm Uri comes in. It's getting really, really cold.
Yeah.
It's about to be Valentine's Day. That's a nice kind of anchor in the conversation.
Yeah.
And then the control room notices it's all about to kick off. And then what actually happened? Because there were blackouts, right? There were blackouts. What caused? Well, we know what caused that, but what happened to make that happen?
Yeah, so we walked through kind of the different maybe contributing factors to the overall difficult situation, right? So, as we get into the night of, I think it's Sunday, February 14th is maybe the day that lived in infamy.
Romantic.
Yes, right. So that's quite the present. My girlfriend, of course, stranded at home in our apartment, and I'm holed up in the hotel waiting to go into work the next day. Quite the Valentine's Day. But you're getting into Sunday night. Temperatures are beginning to drop even further. So we're going from, right around freezing to well below freezing, talking about single digits Fahrenheit, negative Celsius, right? So demand's going through the roof, and getting towards around maybe 11 p.m., I'll say, things are, getting tighter for sure. Conditions are like looking like it's going to be, a tight operating night essentially, as demand's really high, and ERCOT's trying to fulfill that. Kind of an all hands on deck situation. Lots of transmission constraints being dealt with. Trying to make sure all the generation's online essentially as much as possible, and that it's functioning okay. Frequency of course staying around 60 hertz. But that situation is evolving. It's getting tighter and tighter. Grid conditions are getting tighter and tighter. In terms of, you have less and less reserves available in terms of the amount of generation you have to meet additional demand.
You're really kind of reaching down the back of the sofa now, grabbing everything you possibly can.
Yeah.
If you can generate, you're online on the system right now.
Yeah, shaking out the piggy bank for sure. Yeah. And so then kind of all of a sudden, you pretty much, it almost happened simultaneously. You started to see generators have to come offline, whether that was kind of going back to the different factors that we talked about, whether that was a failure at the plant itself, where some sort of mechanical component wasn't functioning anymore because of cold weather or something of that nature. So you had actual power plant trips. You had just runbacks in terms of something's not running right, so we need to reduce power and eventually come offline. And then you also started to see generators say, we don't have any fuel because we're having gas companies declare force majeure, act of God in terms of this crazy weather event. So these contracts that we have are actually undeliverable.
It's not funny, right? Because lots of bad things happened. I mean, people were without power for days.
Yeah.
This includes, critical things like hospitals, and some people sadly died. So it was a tragedy.
Yeah.
But the number of extreme events that happened at once is just remarkable. And so the phone was ringing and people were saying, ERCOT control room, we've got to come offline. And then what? Do you have to choose? Was it planned blackouts? Do you have to say, okay, we're going to have to shed some load here. Who's coming off first?
Yeah. So the way that essentially works is, once you reach a point of, and so I guess to kind of finish off where we were before, so you have all these plants coming off, pretty close proximity to each other. We're talking within minutes and sometimes within seconds of each other. And we're talking about some relatively large combined cycle gas plants where you have, 500 megawatts coming offline pretty rapidly. Or if it's multiple, then you have maybe potentially into the gigawatts of power or supply coming offline pretty quickly. Above all else, the one thing that ERCOT is trying to do is keep grid frequency at 60 hertz, so matching supply and demand.
Mhm.
And all of the complexities around it really go into solving that problem.
The
But
heartbeat.
the heartbeat, right? So if you have all the supply quickly falling off, typically what you would need to do is replace that to make sure that, we're still supplying demand at 60 hertz. But if it's coming off very quickly and it's in these large magnitudes, that's not necessarily easy to do. And so what ended up occurring is frequency started to sag off of 60 hertz. And usually like a pretty large frequency drop is maybe only like zero point 0.1 hertz or, 1/10 or 100 millihertz, something like that. And those are all the same, just for different units.
If you're following,
Yeah,
those
yeah.
three were the same number
Same
with
thing.
different numbers.
Yeah. Just expressed different ways, sometimes within the industry that happens.
And just to get an idea about, so is this happening, is it taking hours? Is it taking minutes?
We're talking about like, this is within minutes now. So I want to say this is getting towards 1 a.m.
Okay.
I don't remember exactly, but yeah, we'll call it that. So yeah, we're talking about within minutes, you have frequency really starting to sag off of 60. But when I say severe sags, kind of for that reference point I had, that 0.1 hertz, right? That would be relatively significant. You'd start to see some reserves beginning to get deployed to restore frequency. But at the actual absolute nadir, frequency was pretty close to like 59.3 hertz. So for context, that's like 0.7 hertz relative to that. Already what would have been relatively significant, 0.1. So that's a huge deal. We're talking about, 7 times more than what's already a relatively significant frequency excursion. So when that happens, if you really wanted to dig through the ERCOT protocols, you could see the timing of, as frequency gets into really severe scenarios, basically how long you have until utility loads or utility demand starts essentially just removing itself, start tripping off. So you have under
circuit breakers opening, you've got timed switches that are saying, I'm going to hang on. If this frequency doesn't fix itself, I'm going to have to drop off.
Have to, for the sake of protecting equipment across the system. And essentially, the actual physical things that are going to be doing that are called under frequency load relays. So they have timing settings to just say, if frequency is below this point, you're going to basically hold off, like you were saying, for this long. And then at that point, you will open the circuit breaker, disconnect this load. And so that kind of the amount of time decreases as frequency gets further away from 60, right? So at like 59.7, that might be I don't know exactly, but dozens of minutes probably. But as you get towards 59.4, 59.3, we're talking about like only a couple of minutes. And I think below 59.3, it's on the order of like seconds.
Cascading. There's a diagram with this cascading effect.
Yeah.
Where you just get, as it gets more extreme, you've got less and less time.
You'd have one of your favorite things on it, logarithmic scales. Yeah.
I do love a logarithmic scale.
Yeah. So essentially, again, going back to our scene, we're talking about frequency being, I want to say it got at its low point to between like 59.3 and 59.4. And I think the number was something like 7 or 8 minutes, essentially, until basically all transmission demand across the system was going to be shed. And we had literally a true blackout and would have to, restart the grid from
like an entire
ground zero.
System blackout.
Yeah.
That is the worst case scenario, isn't it?
The worst case scenario. You're going to have the National Guard deployed to Texas, and people are going to be getting water on street corners and bad. Just the all-time worst case scenario, essentially, right? So you're minutes away from that, basically.
You also have to establish frequency from zero. So the cool thing about the electricity system is there's always a frequency that everyone can, what's the word I'm talking about here? Synchronize to, yeah. But when everything goes to zero, someone's got to start it up again. We have things called Black Start and lots of other contracts like that, but real bad.
Yeah.
So let's not let that happen.
So you're trying to avoid that. And so basically that's, the ERCOT control room, of course, is already well into taking action before this. They're trying to, replace the generation that's been lost. But once you reach this point where you're like, all right, well, we're minutes away from like complete darkness. So we need to get rid of demand to rebalance frequency, right? So I think ultimately it ended up being something like 20 gigawatts at peak outage. That was cut. And a lot of that happened pretty quickly.
Oh my God.
Pretty quickly on that night of February 14th into February 15th.
But it didn't just stop there, right? So 20 gigs came offline-ish.
Yeah.
But then some of these places were out of power, but they didn't have power for days.
Right. So if we go back to all of our generation that was lost and all of our frozen natural gas wellheads, well, they stayed frozen because it was below freezing for 4 or 5 days or whatever. So you still have all these gas contracts that are going undelivered. You still have power plants that had mechanical failures at some point. They just have to get it fixed before they can come back online. They're probably running out of fuel as well. You still have wind generating very low amounts of power. You have solar generating very low amounts of power.
Oh, and power, it's probably worth just noting power prices here. So power prices were, as you'd expect, in a scarcity event,
Yeah.
through the roof.
Through the roof.
So you'd think, so the whole idea is that when power prices go so high, that the system, economics fixes everything, right? Power price goes really high, it encourages everyone to generate, and you kind of solve the problem.
Yeah.
But when there's nothing left in the tank, you can have these really high power prices and nothing to resolve it.
Yeah. Yeah. So the market, of course, was still running, but it was almost like the market was suspended because it was basically just like, if you are able to be online, you will be running essentially as a generator.
I'm getting paid handsomely to do so.
Getting paid like, I think at the time, like $9,000 per megawatt generated. Yeah, and that's on an hourly basis, but pretty much just like never before seen, probably never will be seen again type
Touch wood.
power price events. Yeah, yeah, for real. Yeah.
There's wood being touched.
Might need to legitimately do that, but yeah, it was kind of a true like,
You gonna say it? Say it. Black Swan.
yeah,
Yes.
yeah, we'll call it that. We'll call it a black swan.
I saw a chart on Reddit. Not that I spend a lot of time on Reddit, but I saw a chart on Reddit which is like, you can do Google, you can search Google terms, the usage of black swan as a phrase, like ironically,
Yeah,
it's gone
yeah.
through the roof in the
Yeah.
last 5 years with COVID and
Yeah.
wars and all that stuff. But that's Reddit for you. All right, we talked about Uri. There's a couple more topics I want to talk about briefly. So firstly, let's talk about batteries in ERCOT. What's the state of the nation for batteries in ERCOT? And then I want to ask you your contrarian view, which, I mean, I do already know it, and I think everyone should hear it. It's very interesting. But firstly, batteries in ERCOT, what's the situ?
Yeah, so like I guess kind of to go back to Uri for one more second, we said we had probably only a few hundred megawatts of storage capability at that point. As of now in 2023, it's the end of the year, I think we're over 3,000 megawatts of the build out being both commercially, just both operationally and commercially online. So yeah, and I think as of now, based on ERCOT numbers are a little bit higher, and part of that is because there's a period of time when a resource is online versus when they're actually operating commercially. There's lots of testing that they have to do essentially to get approved for essentially full interconnection and full participation in the market. So their capacity number is going to be a little bit higher than like the EIA or the Energy Infrastructure Administration Agency, something like that. They provide a data set basically just kind of cataloging all the generation across the, I think, entire country, if not continent. And so within ERCOT, their number's a little bit lower.
Just
to summarize,
firstly, kudos to that. That data set is amazing.
Yeah,
I mean,
really
just whoever's responsible for putting that together deserves a big high five.
I think we can thank the U.S. government for that.
Thank the U.S. government.
Yeah. So yeah, it is a great data set, great resource. But essentially, their capacity projection for the end of next year, I want to say, is like 11 or 12 gigawatts of storage.
We've got 8 or 9 in our numbers, haven't we? Something like that.
Yeah.
So yeah, Uri, half a gig online, end of next year, somewhere between 8 and 12 gigs.
Yeah. So to frame that, that's about a little less than 4 years to get to that point. So it's pretty insane build out for sure.
There are lots of batteries connected to ERCOT.
Lots of batteries
now and even more soon. So what happens next?
I think next, the big thing that people have been talking about and will be talking about is ancillary service saturation. So I'm sure a lot of your UK listeners are familiar with that one, but the idea of just typically for storage resources, their entry point into the power market is often to start by just receiving ancillary service contracts, right? So that's providing, your frequency response and your reserves to the grid essentially, and getting compensated to do so. Part of the reason for that is one, because especially for the reserve contracts, you're not going to be deployed all the time. So you can essentially sit idle without actually having any throughput and still get paid for that. So that's valuable to a storage resource where they have essentially a lifespan where, the number of times they cycle, they get less efficient and eventually don't really function quite nearly as well as they did at the beginning of operation. So yeah, to summarize, that's part of why ancillary services are desirable. And often when they're not saturated, storage resources can not quite set the price, but really help drive the price of the service and get pretty well compensated for it. So
Well, just a note on that though.
yeah,
In ERCOT, what's quite unusual from a European lens is that it's not just batteries that are providing these services. There's a load of different participants.
yeah. For example, you have RRS is one of the reserve services within ERCOT, and there's a huge component of that is typically just fulfilled by load resources. And part of that is because there are kind of subtypes of that ancillary service, where specifically one of the subtypes is just at us kind of going back to what we were talking about before, the under frequency load relays. If you reach, I think it's 59.7 hertz or below, all of those load resources are going to be deployed. And what that means is essentially, if you're a big industrial customer and you have an under frequency load relay, you can just say, all right, well, frequency gets that low, which has happened basically one time in quite a long period of time.
It's a blunt instrument, a bit like dynamic, but like demand side response, DSR,
Yeah.
where you trip stuff off and you get paid for it.
Yep, exactly. And it's very
happens.
It basically never happens. So they're pretty much willing to carry it for close to for free because it's just, like, why not? We have this relatively large amount of power demand, so we can get compensated by an additional revenue stream.
Is that going to carry on though, right? Because if you can have dynamic services and a battery can respond, and you don't have the opportunity cost in a battery like you do of switching off an industrial load, do ERCOT even want that service long term, or when batteries can do it better?
I would say yes, because there's room for both of them, and it's kind of just an additional tool in the back pocket, and it's not that specifically that type of ancillary service is really not costing the system very much money.
Yeah,
it's incredibly cheap. So I would say that one in particular, I'd say is pretty safe.
Oh, by the way, if that trip happens, that's going to be at a time of scarcity when those units won't want to be consuming it anyway because price will be so high. You'd think. So, if you're a manufacturing plant and prices go to $9,000, well, it doesn't matter whether you tripped or not. You don't want to be running.
Yeah,
it's almost like
that goes back to if we wanted to get into the bilateral type forward markets, they're probably going to have some kind of off-take contract where they're hedged against that. But yeah, so that there's that component. There's also, as you alluded to, other generation resources, particularly in ancillary services like ECRS and non-spin. So ECRS being the ERCOT Contingency Reserve Service.
Which is the new exciting one.
That is the new one. It started
the new shiny thing.
June of this year. Yeah. So additional ancillary service capacity being awarded, right? So that's fun. More.
It sounded like you didn't think that was fun, and I know for a fact you really think that's fun.
Well, it is and it isn't, right? I mean, it's the not fun part is it costs the grid more money, so there's that. But maybe it's more reserves. That's good. Going back to that, you have thermal generation that can participate in those last two ancillary services because the deployment time that's required by ERCOT, if those services are deployed, is a larger period of time. You have thermal resources that, they're not going to be able to deploy the way a storage resource would be within seconds, obviously, for storage, or nearly instantaneously, really. So the fastest thermal resources are only going to be able to get online in like 10 minutes, and a lot of them would be even more like 30 minutes. Yeah, so you have thermal generation that can participate in those services, essentially. And that makes them more competitive than your regulation and RRS services, which are at this point pretty well dominated by storage. They're not, maybe dominated is a strong word as of now because the participation's been more like 60, 70% rather than 90, 100% in terms of the average amount of contracts being awarded in maybe a given operating month. Essentially, as going back to our build out numbers, as more and more storage comes online, that percentage of contracts being awarded to storage resources should continue to rise theoretically because they want to be awarded ancillary services. And ultimately, there reaches a certain point where there's essentially too much storage capacity to all receive ancillary service awards. The market gets more competitive, drives the prices down.
Musical chairs situation where somebody's going to be left standing up, right? There's not enough contracts to go around. But there's plenty of there's plenty of other ways to make money in the market. There is a huge locational element to that as well, though. Izzy, the producer, is currently giving us signs like we've gone on too long. And I want to ask you the last question, which is, what is your contrarian? You don't need to plug anything because we're on the same side here, but we plug stuff enough as it is. What's the contrarian view? What do you believe that not everybody else does?
Yeah. So one thing we didn't quite get to mention yet was NPR 1186. NPRR, for our last acronym of the day, is
NPRR.
Nodal Protocol Revision Request. So ERCOT has their nodal protocols, which are essentially just the rules by which the grid functions. And a revision request, obviously, just being a request to make a change to the stakeholder process that essentially derives legislation for the grid. That revision request, NPR 1186, was recently approved by the ERCOT Board of Directors. Essentially, what it means is storage resources will have to reserve enough state of charge, so essentially enough energy to fulfill any ancillary service obligation that they have received for that given operating hour. So, if, for example, a storage resource has 5 megawatts of RRS at the beginning of the operating hour in which they hold that responsibility to fulfill that obligation, they need to have 5 megawatt hours of energy stored within their resource. And that then will decrease throughout the operating hour, the obligation that they need to, or the amount of energy that they need to have stored to fulfill their obligation.
So what they're saying is, to put this into,
Yeah.
to paraphrase it a little bit, if I've got this right, what ERCOT is saying is, look, if you want a frequency response contract, that's fine,
Yeah.
but we need to make sure you've got enough gas in the tank or enough energy in your battery to really support frequency for the duration we think that may be necessary if you're going to get paid. The problem is that all sounds very reasonable.
Yeah.
The problem is if you're going to, if that's the requirement, then you don't have as much state of charge to do other stuff at the same time.
Yeah. Yeah. So, I mean, essentially, it all comes back to, theoretically, in the worst case scenario, you might have this ancillary service deployed for the entirety of your operating hour. And ERCOT is just trying to make sure that they're actually going to receive the power that they contracted for a full deployment.
When you say deployed, you mean like the frequency is low for the whole hour,
Yeah.
and you get paid for the hour, and so you have to discharge throughout the whole hour.
Yeah, you're going to have to actually provide that throughput. That's essentially the main component of the rule as of now. There were previously, prior to the legislation being approved, some additional components that were maybe a little bit more restrictive in terms of the amount of ancillary services that storage could qualify for and things of that nature. That's actually not in the legislation anymore. It's been argued out through the stakeholder process, essentially. So at this point, that's
Good news.
yeah.
Because this is all like, let's cut to the chase. This is bad for batteries.
Yeah, in the sense that it's an additional thing they have to do, and it's something else they have to manage, and it's very conservative, right? Because I mean, 99.9% of the time, an ancillary service type is not going to be deployed for an entire operating hour, but that's kind of the battle that's waged in a lot of those stakeholder processes. Is that ERCOT is always trying to protect against that 0.1% as much as they possibly can, because it's not 0%. It is technically feasible. It can happen. And so it kind of clashes with the idea of, probability wise, it's probably not going to happen. Storage resources are just saying, well, hey, what if we only had 90% of our state of charge that we absolutely needed for an entire operating hour? And then if it was actually this crazy event where like we needed every bit of ancillary services deployed, maybe we could move it around our operating fleet. If you're an operator that operates multiple units, we could kind of move that responsibility around. But the problem is it's just kind of a slippery slope where it's just like some participants might be able to operate in certain ways that like could make that work, and some just might not have enough resources. There's just additional complexities that ERCOT can't really guard against, right? So I definitely I know I'm coming from ERCOT, so I have sympathy to that perspective as well. Essentially, going all the way back to what my contrarian
Yeah, what's the contrarian bit? You've described something that's really bad for batteries, right?
Yeah, but my contrarian view
comes.
is that it's not actually that big of a deal.
You heard it here first.
Yeah. Yeah. So essentially, one, this is something they were probably already more or less doing, is essentially having enough energy within a given storage resource to actually meet their ancillary service obligation. Because if you have a deployment of an ancillary service and you don't fulfill your obligation, theoretically, that could result in a compliance penalty. So you don't want that to happen. You don't want to have to pay for a mistake like that.
You're already doing this math anyway.
Pretty much. Yeah. I mean, and maybe there are some participants out there that are a little bit more aggressive with their state of charge management. And that's kind of what this rule is mostly in place to kind of guard against.
Mentioning no names.
No names. Yeah. But The other component to it is we were just talking about the ancillary service market saturating because we're going to have all this additional storage capacity, right? So, a year from now, you're going to have so much of the storage fleet that has no ancillary service obligation. And even if you are a resource that has an ancillary service obligation, it's probably only going to be a percentage of your overall capacity. And then beyond that, one of the arguments in the stakeholder process from maybe the storage side of things was that, in these extreme scarcity events, over the course of this past summer, we had, some pretty tight days operating on the grid. And you saw storage really contribute to kind of getting through those tight periods. So, often that's driven by solar ramping down in ERCOT and net load. So your demand less wind and solar going pretty high in a short period of time. You kind of have to fulfill the gap that's left by the solar generation with more flexible generation. So, thermal or storage. So you saw
storage with the knight in shining armor many times this summer.
Yeah, it did a great job. Absolutely. And it's an incredibly valuable service to the grid and how flexible it is and how fast it's able to act on those conditions appearing. But one of the arguments was that ERCOT essentially was going to be limiting that in cases like this, where you have those scarcity conditions and you have all of this energy that's tied up in your ancillary service obligations. But I get my perspective on that is that if it's really that tied up an operating condition and grid conditions are that critical, ancillary services are going to be deployed anyway. So you're going to have ECRS and non-spin and RRS.
AS ranks higher anyway, doesn't it? Because we're coming back to this heartbeat thing.
Yeah,
it's
way above the shedding load.
Yeah,
There's also
28
steps in between there theoretically as well. So yeah, if it's tight conditions, ancillary services are going to be deployed, and so with like ECRS and non-spin, for example, the deployment of those involves essentially just a resource releasing that reserved capacity that they had to the economic dispatch, and so they might still not even have to provide the throughput. It's only if they get centrally dispatched by ERCOT. So in my opinion, if it's a true critical situation, the capacity is still going to be there. So in my opinion, that's maybe not quite as significant of an argument. I'm certainly sympathetic to the storage cause, especially in the fact that this is kind of a guarding against the 0.1% type thing. But I'm also coming from maybe more of the operations background where I kind of see the value in that.
What matters is lots of things matter. I was about to describe this as one binary thing, which it isn't.
Yeah.
But one of the things that really matters is the dollar impact, right?
Yeah.
And from what you said earlier, look, if you're building an asset now, the majority of your business case probably isn't ancillary services anyway.
Yeah, and maybe in the very short term it still is. But if you're taking a medium to long term view, ancillary services are only going to be a smaller component of that. And given the suppressed prices in them that are coming in the near future, they're not going to be a significant contributor anymore. You're going to be much more energy arbitrage focused. And beyond that, from like the reliability argument, the capacity is still going to be there. So yeah, going to sum it all up, I think MPRR 1186 is both somewhat necessary and also it's going to be all right for storage resources. I don't think it's going to have that large of an impact to their medium to long-term bottom line.
Excellently framed. And with that, we've reached the end of the podcast. We didn't touch locational marginal pricing much. We didn't touch modeling and forecasting. We hardly talked about other types of generation classes. There's so much we could have talked about, but maybe next time. I want to say a massive thank you for joining us on the podcast and joining us as part of the Modo team.
Yeah.
And if you're listening to this and you haven't yet, please do hit like, subscribe. You get a lot more of this kind of content in your ears once a week. All right. Thanks, everybody. See you soon.